Mars, the red planet, has beckoned humanity for millennia. Its fiery hue, visible even to the naked eye, sparked curiosity and wonder in ancient civilizations. Across cultures, Mars has been intertwined with mythology, war, and the very essence of our existence. Its reddish glow, distinct against the backdrop of the night sky, inspired tales of gods, battles, and cosmic events. The ancient Egyptians, keen observers of the heavens, named it Horus the Red, associating it with their god of war. The Babylonians called it Nergal, their deity of death and pestilence, reflecting its ominous crimson presence. For the Greeks, it was Ares, the god of war, its movements across the sky seen as harbingers of conflict and bloodshed. These early interpretations, while rooted in superstition, underscore the enduring fascination with Mars. Its celestial dance, moving against the fixed backdrop of stars, fueled speculation and ignited imaginations. Was Mars a celestial being, a wandering god, or a distant world harboring secrets yet unknown? The questions surrounding Mars, passed down through generations, laid the foundation for centuries of scientific inquiry. As telescopes improved, our view of the red planet transitioned from a blurry dot to a world with intriguing surface features, further deepening the mystery and fueling the desire to unravel its enigma. Mars, our celestial neighbour, orbits the Sun at an average distance of 142 million miles, placing it as the fourth planet from our star. Its orbit, more elliptical than Earth's, results in significant temperature variations throughout its Martian year, which lasts 687 Earth days. This elongated path around the Sun contributes to a climate quite different from our own, shaping the Martian landscape and influencing its potential for harbouring life. Despite its distance, Mars is relatively close in astronomical terms, making it a prime target for exploration and observation. Its proximity, coupled with its intriguing surface features, has fueled the dreams of reaching out and touching this alien world, of unravelling its secrets and perhaps even one day setting foot on its dusty plains. The red planet's diameter is roughly half that of Earth, and its gravity is significantly weaker, about 38% of Earth's. This difference in gravity would have profound implications for any future human explorers, affecting their physiology and requiring adaptations for long-duration missions. Despite its smaller size, Mars boasts a surface area roughly equivalent to Earth's landmass, offering ample space for exploration and potentially colonization. This vast expanse, painted with shades of red, orange and brown, hints at a dynamic geological past, and possibly a future intertwined with human destiny. As telescopes advanced beyond the rudimentary instruments of the ancients, our view of Mars sharpened, revealing tantalizing details that fueled scientific curiosity. In the 17th century, astronomers like Christian Huygens observed distinct dark and light regions on the Martian surface, suggesting the presence of continents and oceans much like our own planet. Giovanni Schiaparelli, an Italian astronomer, meticulously mapped Mars in the late 19th century, observing what he described as canali, Italian for channels. These features, interpreted by some as artificial canals constructed by intelligent beings, ignited the public imagination and gave rise to widespread speculation about Martian civilizations. Percival Lowell, an American astronomer, became captivated by the idea of Martian canals and dedicated his life to observing and mapping them. He envisioned a dying Martian civilization struggling to survive in a drying world, constructing a vast network of canals to transport water from the polar ice caps to the equatorial regions. While Lowell's theories of intelligent Martians were eventually debunked by improved observations and later spacecraft missions, his work played a crucial role in popularizing the idea of life on Mars. The red planet, once a distant fiery orb, had become a world of possibilities, a potential haven for extraterrestrial life, and a destination for human exploration. The mid-20th century marked the dawn of the space age, ushering in an era of unprecedented exploration that would forever change our understanding of Mars. No longer limited to Earth-based observations, humanity could now send robotic emissaries to the Red Planet, equipped with instruments to study its atmosphere, surface, and potential for life. In 1965, NASA's Mariner 4 spacecraft conducted the first successful flyby of Mars, capturing grainy images that shattered the prevailing image of a lush, Earth-like world. The photos revealed a desolate, cratered landscape, seemingly devoid of the canals and vegetation that had fueled imaginations for decades. Despite the initial disappointment, the Mariner missions, along with subsequent Soviet probes, provided invaluable data that laid the foundation for future exploration. They confirmed the thin Martian atmosphere, primarily composed of carbon dioxide, and measured surface temperatures far colder than previously thought. These early missions, while revealing a harsher reality than many had envisioned, ignited a new wave of scientific inquiry. The focus shifted from searching for intelligent life to understanding the planet's geology, climate, and potential for past or present microbial life. The quest to unravel the mysteries of Mars had truly begun. Section 5: Mars in the Realm of Imagination. While scientific exploration continued to unveil the realities of Mars, its allure in popular culture remained deeply intertwined with imagination and speculation. The Red Planet, once a symbol of war and pestilence, transformed into a canvas for science fiction writers, filmmakers, and artists, reflecting our hopes, fears, and dreams of reaching beyond Earth. H.G. Wells's seminal work, The War of the Worlds, published in 1898, depicted a Martian invasion of Earth, instilling a sense of awe and terror about the possibilities of extraterrestrial life. This iconic novel, later adapted into radio broadcasts and films, cemented Mars's place in popular culture as a source of both fascination and fear. As the space race between the United States and the Soviet Union gained momentum, Mars became a symbol of human ambition and the desire to conquer new frontiers. Science fiction films like Robinson Crusoe on Mars and Mission to Mars explored the challenges and triumphs of human exploration, fueling the dream of one day establishing a human presence on the Red Planet. Even today, Mars continues to captivate our imaginations, serving as a backdrop for countless books, movies, and video games. From the whimsical adventures of Mars Needs Mums to the gritty realism of The Martian, the Red Planet serves as a mirror to our own aspirations, reflecting our desire to explore the unknown, unravel the mysteries of the universe, and perhaps one day find another home among the stars.
A time capsule of catastrophes, Mars, the Red Planet, stands as a testament to time's relentless passage. Its surface is a canvas etched with the scars of billions of years. Mars has been bombarded by asteroids, comets, and meteoroids, each impact leaving its mark on the planet's surface. Mars's geological history is a tale of destruction and creation. Molten rock reshaped the landscape with massive volcanoes. Enigmatic evidence of water hints at a warmer, wetter past. Section 2: The Rise of Olympus Mons and the Tharsis Bulge. Dominating the Martian landscape is Olympus Mons, a shield volcano of staggering proportions. 3 times taller than Mount Everest and covering an area roughly the size of Arizona, Olympus Mons is a testament to the power of Martian volcanism, a colossal mountain built up over eons by layer upon layer of lava flows. Olympus Mons is not alone. It is just one of many volcanoes that cluster in the Tharsis region, a vast volcanic plateau that bulges outward from the Martian surface. This bulge, so massive it actually affects the planet's rotation, is thought to have formed over billions of years as molten rock from the Martian mantle welled up, pushing the crust upward and creating a landscape unlike any other in the solar system. The Tharsis volcanoes, with their gentle slopes and massive calderas, are shield volcanoes, formed by eruptions of relatively fluid lava that spread out over vast distances. These eruptions, likely far less explosive than those seen on Earth, would have released enormous amounts of heat and gases into the Martian atmosphere, contributing to the planet's early climate and perhaps even shaping the conditions for life to emerge. The presence of such massive volcanoes suggests that Mars once possessed a much hotter interior than it does today. As the planet cooled over billions of years, volcanic activity slowed, eventually ceasing altogether, leaving behind a silent, frozen landscape punctuated by the remnants of a fiery past. Section 3. Scars of Impact, Craters Big and Small. Across the Martian surface, craters of all shapes and sizes tell the story of the planet's violent history. Formed by asteroid and comet collisions, these craters offer a glimpse into the early solar system. The Hellas Impact Basin, over 1,400 miles across, is visible from Earth. Smaller craters, like raindrops on a dusty windowpane, dot the Martian surface. Studying these craters helps scientists understand Martian history and potential future impacts on Earth. Waters mark ancient rivers and lost oceans. Mars harbors evidence of a wetter past, with liquid water carving channels, filling lakes, and forming oceans. This ancient water, now ice or lost to space, holds clues to past habitability. Valley networks resemble dried-up riverbeds on Earth. Mars exhibits features suggesting ancient lakes and oceans. Vastitas Borealis may have been a vast ocean. Understanding Mars's water history is crucial for unraveling its past habitability.
Section 1. A thin veil, the breath of a bygone era. Imagine standing on Mars, gazing at a sky tinged with pale pink hues. You'd feel the ground beneath your feet, the cold, dry air against your skin. The Martian atmosphere, a wisp compared to Earth's, exerts a mere fraction of the pressure. This thin veil of gases holds clues to Mars's past and present. Its composition tells a tale of a planet that may have once been warmer and wetter. Over eons, Mars lost much of its atmosphere, stripped away by the solar wind. Understanding the Martian atmosphere is crucial for future exploration. Section 2. Carbon dioxide's reign, a stifling embrace. Inhale deeply on Mars, and you'd be met with a lungful of carbon dioxide, the dominant gas in its atmosphere. Comprising over 95% of its composition, carbon dioxide exerts a powerful influence over the Martian climate, trapping heat and contributing to the planet's extreme temperature swings. This carbon dioxide-rich atmosphere, while toxic to humans, might have played a role in Mars's warmer, wetter past. Some scientists speculate that in its early history, Mars may have experienced a greenhouse effect, with volcanic eruptions releasing carbon dioxide and other greenhouse gases into the atmosphere, trapping heat and allowing liquid water to flow on the surface. However, over billions of years, Mars lost much of its atmosphere, including its greenhouse gases, to space. This loss, likely due to the planet's weak gravity and the stripping effects of the solar wind, resulted in a cooling climate and the disappearance of surface water, transforming Mars into the cold, dry world we see today. Today, the Martian atmosphere's carbon dioxide content fluctuates with the seasons, freezing out into polar ice caps during the Martian winter and sublimating back into the atmosphere during the summer. These seasonal variations in carbon dioxide concentration contribute to the planet's dynamic climate, driving winds, dust storms, and even influencing the distribution of water ice. Section 3. Whispers of nitrogen and argon, trace gases in a tennis hold. While carbon dioxide reigns supreme in the Martian atmosphere, other gases, albeit in minuscule amounts, add their own nuances to this thin veil. Nitrogen, the most abundant gas in Earth's atmosphere, makes up a meager 2 to 3% of the Martian air, a mere whisper compared to its dominance on our planet. Argon, another noble gas, lingers in even smaller quantities, a testament to the Martian atmosphere's tenuous hold on its constituents. These trace gases, while seemingly insignificant, provide valuable clues to the planet's atmospheric evolution, hinting at processes that have shaped its composition over billions of years. The presence of nitrogen, for instance, suggests that Mars may have once possessed a much thicker atmosphere, perhaps even similar in density to Earth's early atmosphere. However, over time, the lighter nitrogen molecules escaped into space, leaving behind a thinner atmosphere dominated by the heavier carbon dioxide. Argon, with its various isotopes, serves as a time capsule, preserving a record of atmospheric loss over time. By studying the ratios of these isotopes, scientists can estimate how much atmosphere Mars has lost over its history and gain insights into the processes that drove this loss. Section 4. The Water Vapor Enigma, Clues to a Wetter Past. In the dry, frigid Martian air, water vapor exists as a fleeting presence, a ghostly reminder of a time when liquid water may have flowed freely on the planet's surface. While the Martian atmosphere contains only trace amounts of water vapor, its presence is a tantalizing clue to the planet's hydrological cycle and its potential for harboring life. Water vapor on Mars is locked in a delicate dance with temperature and pressure, constantly cycling between the atmosphere, the polar ice caps, and the subsurface. During the Martian summer, some of the polar ice caps sublimate, releasing water vapor into the atmosphere, while in the winter it freezes out again, contributing to the growth of the ice caps. The presence of water vapor in the Martian atmosphere, while sparse, has implications for future human exploration. Extracting water from the atmosphere could provide a valuable resource for future Martian colonists, reducing the need to transport large quantities of water from Earth. Moreover, understanding the dynamics of water vapor in the Martian atmosphere is crucial for interpreting data from rovers and landers, as variations in humidity can affect instrument readings and complicate the search for signs of past or present life. Section 5. From dust devils to global storms, atmospheric fury unleashed. Don't be fooled by the Martian atmosphere's thinness. It's capable of unleashing weather events that dwarf anything Earth experiences. From towering dust devils to planet-encompassing dust storms, the Martian atmosphere, though tenuous, is a force to be reckoned with. Dust devils, those swirling vortices of dust, are a common sight on Mars, often reaching heights greater than their terrestrial counterparts. These miniature tornadoes form as sunlight heats the Martian surface, creating rising plumes of warm air that pick up dust and spin into whirling columns. But the true spectacle of Martian weather is the global dust storm, a planet-scale event that can engulf Mars in a shroud of dust for months on end. These storms, driven by a complex interplay of atmospheric circulation, temperature gradients, and dust lifting, can dramatically alter the Martian climate, obscuring the surface from view and influencing global temperatures. While fascinating to observe, these dust storms pose significant challenges for Martian exploration. Dust accumulation on solar panels can cripple robotic missions, while reduced visibility and communication blackouts can hamper operations and jeopardize the safety of future human explorers. Section 6. A leaky shield, escaping to the void. Unlike Earth, with its robust magnetic field that acts as a shield against the onslaught of solar wind, Mars stands exposed, its atmosphere vulnerable to being stripped away by the constant stream of charged particles emanating from the Sun. This atmospheric escape, a slow but relentless process, has played a significant role in shaping Mars's climate and habitability over billions of years. The solar wind, a plasma of charged particles, bombards the Martian atmosphere, stripping away ions and molecules, particularly the lighter ones like hydrogen and oxygen. This process, known as sputtering, gradually erodes the atmosphere, much like sandblasting can wear away at a rock face over time. The lack of a global magnetic field on Mars is a crucial factor in its atmospheric loss. Earth's magnetic field acts as a protective barrier, deflecting the solar wind and preventing it from directly interacting with our atmosphere. Mars, however, lost its global magnetic field early in its history, leaving its atmosphere exposed to the ravages of space weather. This atmospheric escape has had profound consequences for Mars. As the planet lost its atmosphere, its surface pressure decreased, causing liquid water to evaporate or freeze. The loss of greenhouse gases, stripped away by the solar wind, further contributed to the planet's cooling, transforming it into the cold, dry world we see today.
Section 1. A Tale of Two Hemispheres. The Great Dichotomy. Gaze upon a globe of Mars, and you'll notice a striking contrast. A tale of two hemispheres, each bearing the mark of a distinct geological history. This Great Dichotomy, as it's known, divides Mars into two distinct regions: the northern lowlands, smoother and less cratered, and the southern highlands, a rugged and ancient terrain. This stark division, a defining feature of Martian topography, has puzzled scientists for decades. Theories abound, some suggesting a colossal impact early in Mars's history, while others point to internal geological processes, perhaps akin to plate tectonics on Earth, but far less active. The northern lowlands, lying several kilometers lower in elevation than the southern highlands, hint at a past where water may have pooled, forming vast oceans or seas. This region's smoother surface, less pockmarked by impact craters, suggests younger terrain, perhaps reshaped by volcanic activity or erosion from ancient water flows. In contrast, the southern highlands stand as a testament to time's relentless battering. Heavily cratered and ancient, this region bears the scars of billions of years of impacts, a stark reminder of the violent early solar system. The highlands' rugged terrain, with its towering mountains and deep canyons, speaks of a more dynamic geological past, shaped by both internal and external forces. Section 2. Northern Lowlands, Echoes of Ancient Oceans. Imagine a time when the northern plains of Mars, now dry and dusty, were submerged beneath a vast, salty ocean. It's a tantalizing possibility, supported by intriguing evidence that points to a wetter, warmer past for the red planet. The northern lowlands, with their smooth, low-lying plains, hold some of the most compelling evidence for a past Martian ocean. The region's elevation, significantly lower than the southern highlands, suggests a natural basin where water could have collected. Scientists have found hints of ancient shorelines etched into the Martian terrain that may have once marked the boundary between land and sea. These features, while subtle and eroded by time, suggest the presence of a long-lived body of water, perhaps lasting for millions or even billions of years. Furthermore, the composition of the northern lowlands, rich in minerals that form in the presence of water, supports the idea of a past ocean. Clay minerals, sulfates, and other hydrated minerals detected by orbiting spacecraft and rovers paint a picture of a wetter past, a time when Mars may have been more hospitable to life. Section 3. Southern Highlands, a battered and cratered realm. Step onto the southern highlands of Mars, and you'll be transported back in time to an era when the solar system was a more chaotic and violent place. Here, impact craters, some dating back billions of years, dominate the landscape, bearing witness to the relentless bombardment that shaped the early planets. The southern highlands, older and more heavily cratered than the northern lowlands, offer a glimpse into the early solar system, a time of frequent collisions as planets formed and evolved. The craters, ranging in size from small depressions to vast impact basins hundreds of kilometers across, tell a story of cosmic violence, each impact leaving its mark on the Martian surface. These impact craters, while testaments to destruction, also provide valuable scientific insights. By studying their distribution, size, and age, scientists can piece together the history of impacts on Mars, estimating the rate of collisions over time and understanding the processes that shaped the planet's surface. The highlands' rugged terrain, with its towering mountains and deep canyons, further reflects its ancient origins. Shaped by a combination of impact cratering, volcanic activity, and erosion, this region stands in stark contrast to the smoother, younger plains of the north, highlighting the dramatic dichotomy that defines Martian geology. Section 4. Tharsis, a volcanic wonderland. Rising from the Martian plains, the Tharsis region is a volcanic wonderland with some of the largest volcanoes in the solar system. At its heart lies Olympus Mons, a shield volcano of staggering proportions. 3 times taller than Mount Everest, Olympus Mons is a true behemoth. It's joined by Ascraeus Mons, Pavonis Mons, and Arsia Mons, known as the Tharsis Montes. The Tharsis region, with its massive volcanoes and vast lava plains, is a testament to Mars' fiery past. Section 5. Valles Marineris, a canyon of superlative proportions. Imagine a canyon so grand, so vast, that it dwarfs anything found on Earth. A chasm that stretches across continents, a scar so immense it can be seen from space. This is Valles Marineris, the grandest canyon in the solar system, a testament to the immense tectonic forces that once shaped the red planet. Stretching over 2,500 miles long, up to 400 miles wide, and plunging to depths of over 4 miles, Valles Marineris is a truly awe-inspiring feature. To put its scale in perspective, it would span the entire continental United States. The Grand Canyon, a mere sliver in comparison, could easily get lost within one of Valles Marineris' side canyons. Unlike the Grand Canyon, carved by the relentless erosive power of the Colorado River, Valles Marineris is thought to have formed through a combination of tectonic activity and erosion. The canyon's formation likely began billions of years ago, as the Tharsis region, with its massive volcanoes, bulged upward, putting immense stress on the surrounding crust. This stress caused the crust to crack and fault, creating a vast rift system that eventually widened and deepened over time. Erosion, primarily from landslides and wind, further sculpted the canyon, carving its intricate network of channels, mesas, and cliffs, creating a landscape of unparalleled grandeur and scientific intrigue. Section 6. Impact craters, windows into the past. Scattered across the Martian surface like cosmic battle scars, impact craters tell a tale of ancient collisions, a time when asteroids and comets rained down upon the young planets. These craters, ranging in size from small depressions to vast basins hundreds of kilometers across, provide windows into the past, offering clues about the early solar system and the processes that shaped Mars. Some impact craters, like the Hellas Basin, are so large they dominate entire regions of the planet. Hellas, with its diameter of over 1,400 miles and depth of over 5 miles, is one of the largest impact structures in the solar system, a testament to the immense energy released during these ancient collisions. Impact craters come in a variety of shapes and sizes, each with its own story to tell. Some craters are relatively pristine, their features well preserved over billions of years. Others have been eroded by wind and water, their rims softened and floors filled with sediment. Some even show signs of past volcanic activity or glacial modification. By studying the distribution, size, and morphology of impact craters, scientists can learn about the history of impacts on Mars, the composition of the planet's crust, and the processes that have shaped the surface over time. Impact craters are like time capsules, offering glimpses into the past and providing valuable insights into the evolution of Mars and the solar system as a whole. Section 7. Polar ice caps, frozen reservoirs of time. At the frigid poles of Mars lie gleaming white crowns, vast ice caps that hold clues to the planet's climate history and the potential for past or present life. These frozen reservoirs, composed primarily of water ice with a seasonal dusting of carbon dioxide frost, play a vital role in the Martian climate. The Martian polar ice caps grow and shrink with the seasons, expanding during the long, cold winters and receding during the warmer summer months. As temperatures drop, carbon dioxide from the atmosphere freezes out, forming a layer of dry ice over the permanent water ice caps. In the summer, this dry ice sublimates back into the atmosphere, revealing the underlying water ice. The polar ice caps are not just static features. They exhibit dynamic processes that shape their appearance and composition. Spiral troughs, carved into the ice caps by wind and sublimation, create striking patterns visible from orbit. Layers within the ice caps, like tree rings, record past climate variations, preserving a history of Martian climate change over millions of years. Studying the Martian polar ice caps is crucial for understanding the planet's climate history, its water cycle, and the potential for past or present life. The ice caps hold a record of past atmospheric conditions, including the presence of greenhouse gases and dust. They also contain water, a vital ingredient for life as we know it, making them prime targets in the search for signs of past or present Martian life. Section 8. Shifting sands, dunes, dust devils, and the power of wind. Across the Martian surface, winds whip fine dust into a frenzy, sculpting dunes, swirling dust devils, and carving intricate patterns into the landscape. Wind, a constant presence on Mars, plays a vital role in shaping the planet's surface, transporting dust, eroding rock, and even influencing the Martian climate. Martian dunes, sculpted by winds over eons, take on a variety of forms, from crescent-shaped Barchan dunes to linear Ceph dunes, each revealing the direction and strength of prevailing winds. These dunes, often found in craters and other low-lying areas, migrate over time, their movements tracked by orbiting spacecraft, providing insights into Martian wind patterns. Dust devils, those swirling vortices of dust, are a common sight on Mars, often reaching heights far greater than their terrestrial counterparts. These miniature tornadoes form as sunlight heats the Martian surface, creating rising plumes of warm air that pick up dust and spin into whirling columns visible from orbit. Wind also plays a role in the formation of global dust storms, those planet-encompassing events that can engulf Mars in a shroud of dust for months on end. These storms, driven by a complex interplay of atmospheric circulation, temperature gradients, and dust lifting, can dramatically alter the Martian climate, obscuring the surface from view and influencing global temperatures.
The quest for liquid water, a Martian enigma. Water, the elixir of life, drives our exploration of Mars. Mars harbors clues suggesting a past where water flowed freely. But finding liquid water today is challenging. Mars's thin, frigid atmosphere makes liquid water scarce. Any liquid water would rapidly evaporate or freeze. The average temperature is -63 degrees Celsius. Yet, scientists haven't given up hope. Evidence suggests liquid water might exist in hidden forms. From recurring slope lineae to subsurface aquifers, the quest continues. Section 2. Polar Ice Caps. Frozen treasures at the Martian poles. At the frigid poles of Mars, vast ice caps hold clues to the planet's climate history and water cycle. These frozen reservoirs influence global temperatures and atmospheric circulation. The ice caps grow and shrink with the seasons, expanding in winter and receding in summer. In summer, dry ice sublimates, revealing the underlying water ice. Spiral troughs create striking patterns visible from orbit. Layers within the ice caps record past climate variations. Section 3. Glaciers, frozen rivers of a bygone era. Imagine a time when glaciers, those slow-moving rivers of ice, flowed across the Martian landscape. Evidence of their past presence is etched into the planet's surface, offering clues to its climate history. Scientists have identified numerous features on Mars that bear the hallmarks of glacial activity. These features are found in various locations, suggesting glaciers shaped the planet's surface. Section 4. Permafrost, a subsurface reservoir of ice and time. Beneath the dusty surface of Mars lies a hidden realm, a subsurface layer of perpetually frozen ground known as permafrost. This frozen reservoir, extending from the polar regions to the mid-latitudes, holds not only a significant amount of water ice, but also clues to Mars's past climate, its geological history, and perhaps even the potential for past or present life. Permafrost forms when ground temperatures remain below freezing for extended periods, typically for 2 years or more. On Mars, permafrost is thought to be widespread, extending to depths of hundreds of meters in some areas. The presence of permafrost has significant implications for our understanding of Mars's water cycle and its potential habitability. The ice within permafrost represents a potential resource for future human exploration, providing a source of water for drinking, agriculture, and even rocket fuel. However, accessing this ice would require developing technologies capable of drilling and extracting water from the Martian subsurface. Permafrost also acts as a time capsule, preserving organic molecules, microbes, and other potential biosignatures from the distant past. Studying Martian permafrost could provide insights into the planet's past habitability, the potential for life to have existed on early Mars, and the challenges of preserving biosignatures in extreme environments. Section 5. Recurring Slope, Linear, RSL, Hints of Transient Flows. In the annals of Martian mysteries, few discoveries have sparked as much excitement and debate as recurring slope lineae, RSL. These enigmatic features, dark streaks that appear seasonally on Martian slopes, have tantalized scientists as potential evidence of liquid water flowing on the red planet today. RSL appear as narrow, dark streaks that lengthen and darken down steep slopes during the warmer months on Mars, fading away during the colder seasons. These features, typically less than 5 meters wide and up to hundreds of meters long, were first observed in high-resolution images taken by the High-Resolution Imaging Science Experiment, HiRISE, camera on NASA's Mars Reconnaissance Orbiter. The leading hypothesis for the formation of RSL is that they result from the flow of briny water, water with a high salt content, which lowers its freezing point, allowing it to remain liquid even at Martian temperatures. As this briny water flows down slope, it darkens the surface, creating the characteristic streaks observed from orbit. The potential for liquid water on Mars, even in transient and salty forms, has profound implications for the planet's habitability and the search for life. Liquid water is essential for all known life, and its presence on Mars today would suggest that the planet is not the dry, desolate world we once thought it to be. Ancient water. Evidence from a warmer, wetter past. Mars bears undeniable scars of a wetter, warmer past, with rivers, lakes, and perhaps oceans. Evidence is etched into the landscape, from lake beds to intricate valley networks. Valley networks resemble dried-up riverbeds on Earth. Found primarily in the southern highlands, they suggest rain or melting snow once flowed. Mars also exhibits features suggesting ancient lakes and oceans. Vast plains show signs of sedimentary layering, indicating long-standing water. Vastitas. Borealis may have been a vast ocean. Hydrated minerals in rocks and soils provide further evidence of past water. The fate of Martian water. Lost to space, locked in ice. Mars, once a water-rich world, is now a dry, desolate planet. Over billions of years, a significant portion of its water has been lost to space, stripped away by the solar wind, while the remaining water is largely locked away as ice in the polar ice caps, glaciers, and permafrost. The loss of Mars's atmosphere, due to its weak gravity and the lack of a global magnetic field, played a crucial role in the planet's water loss. As the atmosphere thinned, the planet's surface pressure decreased, causing liquid water to evaporate more readily. Ultraviolet radiation from the sun, no longer shielded by a thick atmosphere, broke down water molecules in the upper atmosphere, allowing hydrogen and oxygen to escape into space. While a significant amount of water has been lost to space, a substantial volume remains on Mars, primarily in the form of ice. The polar ice caps, glaciers, and permafrost represent vast reservoirs of frozen water, holding the potential to unlock clues about Mars's past climate, its water cycle, and even the possibility of past or present life. Understanding the fate of Martian water is crucial for unraveling the planet's history, its potential for habitability, and the challenges of future human exploration. By studying the processes that led to Mars's water loss, we can gain insights into the evolution of planetary atmospheres, the factors that influence planetary habitability, and the importance of protecting our own planet's precious water resources. Water and the search for life. A cosmic connection. The search for water on Mars is linked to the search for life beyond Earth. Water is essential for all known life forms. The presence of water is a key requirement for habitability. Evidence of past liquid water on Mars fuels speculation of past life.
Step out onto the surface of Mars and you'll be greeted by a stark, otherworldly beauty. Mars possesses a climate of extremes, driven by its thin atmosphere. Imagine standing on a planet where the air is thin and the temperature swings wildly. This thin atmosphere, primarily composed of carbon dioxide, traps some heat from the sun. As a result, Mars experiences dramatic temperature fluctuations. The thin Martian atmosphere also contributes to extreme weather events. Picture a year on Mars, nearly twice as long as an Earth year. At 687 Earth days, seasons are twice as long. Mars's eccentric orbit creates significant temperature and sunlight variations. During perihelion, Mars warms, triggering planet-wide dust storms. During aphelion, it cools, especially in the northern hemisphere. Mars's elliptical orbit and axial tilt create distinct seasons. The Martian day or sol lasts just over 24 hours and 39 minutes. This similarity in day length would be familiar for future explorers. As the Martian year progresses, a deep freeze envelops the red planet, transforming it into a world of ice and frost. Winter on Mars is a time of stillness. As temperatures plummet and winds howl, temperatures can drop to -200 degrees Fahrenheit, posing challenges for life and robotic explorers. The polar regions experience dramatic changes, with dry ice forming over water ice caps, influencing the Martian climate. Section 4. A fleeting thaw, summer's gentle touch. As Mars continues its elliptical journey around the Sun and draws closer during its perihelion, a subtle warmth spreads across the red planet, bringing with it a fleeting thaw and a surge of energy. Summer on Mars, while still chilly compared to Earth, brings with it a touch of warmth, melting some of the carbon dioxide ice, revealing the rusty hues of the Martian soil and triggering a flurry of atmospheric activity. During the Martian summer, temperatures can rise to a balmy 70 degrees Fahrenheit or 20 degrees Celsius near the equator, a stark contrast to the frigid temperatures of winter. While still chilly compared to Earth's tropical regions, this relative warmth creates conditions that could potentially support liquid water, albeit briefly and in specific locations. The polar ice caps, which expanded during the winter, begin to shrink as carbon dioxide ice sublimates back into the atmosphere. This sublimation process releases vast amounts of carbon dioxide gas, increasing atmospheric pressure and driving winds that whip across the planet, sometimes triggering regional or even global dust storms. Summer on Mars is a time of change as the planet awakens from its winter slumber. The increased sunlight intensity, warmer temperatures, and dynamic atmospheric activity create a more energetic environment, albeit still harsh and unforgiving. While summer on Mars may not bring about lush vegetation or flowing rivers, it does offer a glimpse of a more dynamic and potentially habitable world. Section 5. The Fury of Dust, Global Storms and Atmospheric Upheaval. Imagine a planet engulfed in a shroud of dust, its surface obscured from view, its atmosphere choked with fine particles that blot out the sun. This is the reality of a Martian global dust storm, a planet-scale weather event that can engulf Mars in reddish haze for months on end, dramatically altering its climate and posing significant challenges for exploration. Martian dust storms are not uncommon, but global dust storms, those that envelop the entire planet, are relatively rare, occurring every few Martian years. These storms are triggered by a complex interplay of factors, including the planet's elliptical orbit, its axial tilt, and the amount of dust present in the atmosphere. As dust is lifted into the atmosphere by winds, it absorbs sunlight, warming the air and creating updrafts that lift even more dust. This positive feedback loop can lead to a runaway effect, with dust storms growing rapidly in size and intensity, eventually engulfing the entire planet. Global dust storms have a profound impact on the Martian climate. The thick dust clouds block sunlight from reaching the surface, causing temperatures to drop. The dust also absorbs heat, warming the atmosphere and altering atmospheric circulation patterns. These storms can persist for months, significantly affecting the Martian environment and posing challenges for robotic missions and future human exploration. Section 6. Dust Devils Dance, Vortices of Martian Dust. Across the desolate plains of Mars, whirling vortices of dust, known as dust devils, dance across the landscape, their sinuous forms casting fleeting shadows on the reddish soil. These miniature tornadoes, a common sight on Mars, are a testament to the power of the sun to drive atmospheric circulation, even in the thin Martian air. Dust devils form when sunlight heats the Martian surface unevenly, creating pockets of warm air that rise rapidly, creating updrafts. As these updrafts spin, they pick up dust from the surface, forming swirling columns of dust that can reach heights of up to several kilometers. Dust devils are a common sight on Mars, particularly during the spring and summer months when solar heating is most intense. They play a role in the Martian dust cycle, lifting dust from the surface and injecting it into the atmosphere, where it can be transported by winds and contribute to the formation of regional or even global dust storms. While dust devils pose little threat to robotic missions, they could pose a challenge for future human explorers. The dust they lift could interfere with delicate equipment, reduce visibility, and potentially carry harmful static electricity. Understanding the dynamics of dust devils and their potential impact on human activities will be crucial for planning future missions to the Red Planet. Inhale deeply on Mars, and you'd be met not with the life-giving breath of oxygen, but with a toxic brew of carbon dioxide, a gas that would quickly render you unconscious and, if not addressed, prove fatal. The Martian atmosphere, while thin, is a hostile environment for humans, lacking sufficient oxygen to support human life and posing significant challenges for exploration and potential colonization. The Martian atmosphere is primarily composed of carbon dioxide, making up over 95% of its volume. Oxygen, the gas we need to breathe, is present only in trace amounts, far too low to support human life. Nitrogen, the most abundant gas in Earth's atmosphere, is present on Mars, but in much smaller quantities. Breathing the Martian atmosphere without a spacesuit or a specialized habitat would be fatal. The high concentration of carbon dioxide would quickly overwhelm the body, displacing oxygen in the bloodstream and leading to asphyxiation. Furthermore, the thin atmosphere offers little protection from the sun's harmful radiation, posing additional risks to human health. Overcoming the challenges of the Martian atmosphere is crucial for human exploration and potential colonization. Future missions will require innovative technologies to extract oxygen from the Martian atmosphere or transport it from Earth, as well as to create pressurized habitats with breathable air. Developing sustainable life support systems will be essential for establishing a human presence on the Red Planet. Mars, once a world with flowing water and a thicker atmosphere, now stands as a stark reminder of the fragility of planetary climates. The Red Planet's transformation into a cold, dry desert world offers a sobering glimpse into the potential consequences of climate change. Over billions of years, Mars lost much of its atmosphere to space, leading to a runaway cooling effect. Mars's fate serves as a cautionary tale about the importance of protecting our own planet's atmosphere and climate.
The question of life beyond Earth finds a focal point in our exploration of Mars. The Red Planet, once thought lifeless, now beckons with the possibility that life may have existed there. The search for life on Mars is driven by our curiosity about our place in the cosmos. Mars offers a unique opportunity to address this profound question. Evidence of past water suggests Mars may have had conditions for life. Following the water. The hunt for Martian habitats. The mantra of Martian exploration, "Follow the water," underscores the potential for life. Water is essential for all known life forms. The hunt for liquid water guides our exploration. Evidence for past liquid water is widespread. These features tell a story of a warmer, wetter past. Today, the search focuses on areas with potential present-day water. Recurring slope lineae hint at transient flows of briny water. Subsurface aquifers could harbor reservoirs of liquid water. The hunt for Martian habitats includes water-ice environments. Icy regions could harbor microbial life or preserve evidence of past life.
The rover Vanguard exploring Mars. One rock at a time. Mars rovers are our vanguard, exploring the red planet, conducting experiments, and beaming back revolutionary data. Equipped with scientific instruments, they investigate Mars' geology, climate, and potential for life. From Sojourner to Perseverance, each rover builds on the successes of its predecessors, uncovering new secrets.
Signs of life. Biosignatures and the Martian enigma. The search for life on Mars hinges on the detection of biosignatures, telltale signs of past or present biological activity. These signs, often subtle and open to interpretation, could range from fossilized microbes to organic molecules to isotopic ratios that indicate biological processes. The challenge for scientists is to distinguish between biosignatures and abiotic processes, those that do not involve life, which can mimic the signs of life. One category of biosignatures includes morphological fossils, the preserved shapes of ancient organisms or their traces. On Earth, fossilized stromatolites, layered structures formed by microbial communities, provide some of the earliest evidence of life. Finding similar structures on Mars would be a compelling, though not definitive, indication of past life. Another category of biosignatures involves organic molecules, the building blocks of life as we know it. Organic molecules, such as amino acids, lipids, and nucleic acids, are essential components of living organisms. Detecting these molecules on Mars, particularly in high concentrations or in specific patterns, could indicate past or present life. Scientists are also looking for isotopic anomalies as potential biosignatures. Isotopes are atoms of the same element that have different numbers of neutrons. Biological processes can preferentially incorporate certain isotopes over others, leaving behind a distinct isotopic signature. Finding isotopic anomalies in Martian rocks or gases could provide evidence of past biological activity. In the thin Martian air, where every molecule tells a story, the presence of methane has emerged as one of the most intriguing and debated mysteries. Methane, a simple organic molecule, can be produced by both biological and geological processes, making its presence on Mars a tantalizing, though not conclusive, hint of potential life. On Earth, methane is primarily produced by biological activity, such as the decomposition of organic matter by microbes. However, it can also be released through geological processes, such as volcanic eruptions or reactions between water and certain types of rocks. The detection of methane in the Martian atmosphere, first by telescopic observations from Earth and later confirmed by the Curiosity rover, sparked intense excitement and speculation about the possibility of microbial life on Mars. The rover's measurements revealed seasonal variations in methane levels, with peaks in the warmer months and dips in the colder months, further adding to the intrigue. The source of Martian methane remains a subject of ongoing research and debate. While biological activity is one possibility, scientists are also exploring abiotic explanations, such as the release of methane from underground reservoirs, or reactions between sunlight and surface materials. Unraveling the methane mystery is crucial for understanding the potential for life on Mars and the processes that shape its atmosphere.
The dream of sending humans to Mars, a dream that has captivated humanity for generations, is inching closer to reality as space agencies and private companies around the world develop ambitious plans for human missions to the Red Planet. The challenges of such a mission are immense, requiring technological advancements, international collaboration, and a spirit of exploration and adventure that has defined humanity's greatest achievements. A human mission to Mars would be the ultimate test of human ingenuity and resilience. The journey to Mars, lasting several months, would expose astronauts to the hazards of deep space, including radiation, microgravity, and the psychological challenges of prolonged isolation. Upon arriving on Mars, astronauts would face the daunting task of living and working in a hostile environment. The thin Martian atmosphere, lack of liquid water, and extreme temperature swings would require specialized habitats, spacesuits, and life support systems to ensure their survival. Despite the challenges, the scientific and technological rewards of a human mission to Mars are immeasurable. Astronauts, with their ability to make real-time decisions, conduct complex experiments, and explore vast areas, would revolutionize our understanding of the Red Planet. A human presence on Mars would mark a new era of exploration, opening up possibilities for scientific discovery, resource utilization, and perhaps even the establishment of a permanent human presence on another world.
Mars, with its evocative red hue and enigmatic features, has long been a fertile ground for speculation, conspiracy theories, and imaginative tales of ancient civilizations and extraterrestrial life. While scientific exploration continues to unravel the planet's mysteries, revealing a world shaped by natural forces rather than alien architects, conspiracy theories persist, fueled by a mix of genuine curiosity, distrust of authority, and a desire to believe in the extraordinary. One enduring conspiracy theory centers on the face on Mars, a rock formation in the Cydonia region that, in early low-resolution images, resembled a human face, while subsequent high-resolution images revealed it to be a natural mesa, shaped by wind and erosion. Some continue to believe it is evidence of an ancient Martian civilization. Other conspiracy theories suggest that NASA is covering up evidence of life on Mars, hiding the truth about alien artifacts or even secret human bases on the planet. These theories often point to anomalies in images such as unusual rock formations or patterns as proof of extraterrestrial activity or government deception. While conspiracy theories can be entertaining and thought-provoking, it's important to approach them with a critical eye. Extraordinary claims require extraordinary evidence, and the burden of proof lies with those making the claims. Scientific exploration, with its rigorous methods and peer-reviewed findings, remains our most reliable tool for understanding the universe and separating fact from fiction.
Section 8. A new era of discovery, unlocking Mars's secrets. We stand at the cusp of a new era of Martian exploration, marked by sophisticated robotic missions and ambitious human exploration plans. The coming decades promise unprecedented discovery as we delve deeper into Mars's past and pave the way for human presence. Robotic missions will continue to play a vital role, acting as scouts and surveyors. Future rovers will explore new regions, searching for signs of life. The dream of sending humans to Mars is now within our grasp. Space agencies and private companies are developing the needed technologies. Mars exploration is a testament to human ingenuity and curiosity. Mars will continue to beckon, challenging us to push the boundaries of knowledge. As we conclude our journey across the stark yet captivating landscapes of Mars, a sense of awe and wonder lingers. The Red Planet, once a distant point of light, has transformed into a world of its own, igniting our imaginations. From towering volcanoes to ancient riverbeds, Mars whispers tales of a dynamic past. Our rovers have revolutionized our understanding of this alien world. Mars is shaped by volcanic eruptions, flowing water, and relentless winds. The search for life on Mars continues with renewed vigor. Discovering microbial life would fundamentally alter our understanding of life's place in the universe. The dream of sending humans to Mars is now within our grasp, fueled by technological advancements and an unwavering spirit of adventure. The story of Mars is a tale of two planets, one that was and one that is. Billions of years ago, Mars may have resembled a young Earth. But over time, Mars underwent a dramatic transformation, losing much of its atmosphere. What caused this dramatic shift in the Martian climate? Scientists believe a combination of factors played a role, including the planet's small size and weak gravity. As Mars lost its atmosphere, its surface pressure decreased, causing liquid water to evaporate or freeze. The loss of greenhouse gases further contributed to the planet's cooling. Studying Mars's past climate holds valuable lessons for understanding our own planet. By studying Mars, we gain insights into planetary habitability and the consequences of altering Earth's climate. Mars serves as a reminder that even stable planetary environments can change dramatically over time. The future of Mars exploration is a tapestry woven with ambitious plans, technological innovation, and a spirit of international collaboration. Our understanding of Mars will deepen with sophisticated robotic missions and the prospect of human exploration. Robotic missions will act as our scouts and scientific investigators. Future rovers will drill deeper, collecting samples and searching for signs of life. The dream of sending humans to Mars is now within reach. Space agencies and private companies are developing the technologies needed to make this dream a reality. A human mission to Mars would mark a pivotal moment in human history. The exploration of Mars is more than just a scientific endeavor, it's a reflection of our place in the cosmos. As we gaze across the vast expanse of space, we are filled with a sense of wonder and humility. Mars reminds us of the fragility of our own planet. The search for life beyond Earth speaks to our deep-seated curiosity. Are we alone in the universe, or is life a common phenomenon? As we continue our exploration, we carry the hopes and dreams of humanity and inspire future generations to explore